Welcome to Math 104, Chapter 2.1, where we talk about algebraic and graphical solving of linear equations. So just as we got comfortable with the fractions, they're now coming back to us in a big way. Notice that on either side of the equation on your first example, we have fractions. Now, it is totally up to you if you want to do it the algebraic way or if you want to do it graphically. Feel free to just pick one and just get practice with it and do really um, get really good at it. So we do have a step-by-step if you are going to do it algebraically. It says if an equation has fractions. Now this was an error. There's nothing in the blank. It should have been multiply all values by a common multiple, or make all the values have a common denominator and then cancel them out. So big idea on this first step is to get your denominators to cancel, or get fractions out. Get rid of your fractions. So a couple ways that you can do that. So remove any parentheses by distributing. So any parentheses, make sure you distribute throughout that whole parentheses on the inside. Step 3, move all terms with the variable to one side of the equal sign, just as we did on your very last problem of the previous lecture. Combine all like terms. Anything that looks alike can come together, and then isolate the variable by dividing or multiplying by the coefficient. So divide if you see a multiplication. If you see a division, then you can multiply. So let's try it on this first one. It says solve, and we have two sides of the equal sign with multiple different fractions. So first thing we can do is, and I'll show you two different ways to do it algebraically, is either to multiply all of these values by a common multiple. So I do want to try and have you guys change this value too, because students a lot with whole numbers, because they don't look like fractions, a lot of students unbalance their equation because they don't bother to manipulate this one. This one, let's place over 1 so that it looks like it is a fraction. And so you're unlikely to unbalance it by not multiplying that one as well. So what do 3, 5, and 1, what can they all end up multiplying into? What is their least common denominator? Now, if you have a hard time finding a least common denominator, you can always try and find a common denominator by multiplying all of your denominators together. So 5 times 3 times 1 makes 15. Now, this actually happens to be your least common denominator, but it is a good rule of thumb. If you can't think of anything, just multiply together, and there you have something in common. So how does this 5 become a 15? And I'm just going to rewrite, I'm going to rewrite your expression right here. All right, so how does this 5 become a 15? We said we're going to multiply this 5 by a 3. And notice that by multiplying this whole expression, this one's a little different. We haven't encountered it before. We want to make sure we put parentheses around it and put a multiplication sign. Okay, and we'll leave it for a moment. How does this 3 become a 15? Multiply it by 5, and same thing with the 1. Oh, not by 5, by 15. So then we have 2x minus 3 over 15 is equal to 5x over 15 plus 15 over 15. So you have all of the same denominator, which is really nice. This is why this is my go-to method when I teach fractions, is that because your denominators are all balanced, that means we can go ahead and ignore them and cross them out. They no longer apply because everything at the very top is equal. So now have we tackled an equation slightly like this, or is it at least feeling a little bit more approachable? I hope so. We can then distribute in that 3, 4, 6x minus 9 is equal to 5x plus 15. And let's go ahead and combine your like terms. We can subtract your 5x to the other side. And we can go ahead and add 9. Oops. So we get x is equal to 15 plus 9 is equal to 24. So x is equal to 24. So this is my favorite way to get rid of fractions pretty quickly. You can also multiply all of them by a common multiple. Again, your common multiple in this first case was 15. So I'll show you it a little differently if we were going to do it that way. I'm going to put all of this, because it is 2 terms on that right side, into parentheses. And when you figure out what your common multiple is, whether it's the least common multiple or just a multiple, and again, I'm actually going to put the other term in parentheses, you're going to multiply it on either side. So 15 times that whole expression, and again, 15 times the whole expression to the other side. And then we can have 15 times 2x minus 3 over 5 is equal to, and then again, distributing that 15 to both sides, 15x over 3 plus 15. Now we can go ahead and see if anything can cancel before doing any sort of distribution. So notice that 15 and 5 do have some values in common. They both have a 5, which means a 3 gets left behind. Same thing here, 15 divided by 3 is 5x plus 15. Now we have seen that expression before. These are the exact same, which means when we go to solve it, we will end up with x is equal to 24. So depending on which one you feel most comfortable with, feel free to just pick which one is the better of the two. So now let's try it graphically. So because we have 2 sides of the equal sign, we can actually break this expression up. So if I were to rewrite this, 2x minus 3 over 5 is equal to x over 3 plus 1. So because you have 2 sides of the equal sign and they're set equal to each other, we can just pull it apart and make 2. Let's say this is that y equals 2x minus 3y over 5. So that is one of your y's. And the other one, y equals x over 3 plus 1, is another side of the equal sign. So now what we're going to do when we graph both of these together on one graph, we're going to see an intersection. So make sure you see the intersection, and then wherever they intersect, that is actually going to be our answer. So I'm going to do it on both of my calculators. So y equals, and I'm going to put this in parentheses, 2x minus 3 divided by 5. So that is one of my graphs. The following graph, we have y equals x over 3 plus 1. Okay, so when I get out of this, Notice that we do not see our intersection, so we have to determine where it is. So on which side of my graph, my left or my right side, do I think an intersection is going to lie? Well, that just means it's to the right side of my graph. Notice how the lines are getting a little bit closer. So we can actually go ahead and either move it with our fingers, or more likely, we're going to have to manipulate your values. So I'm not so much, I mean, we can certainly change your Y, but I definitely want to get more right. So that means your X maximum has to change. We need to get a little higher than 10. Now keep in mind, we already know your answer. So let's say we didn't though. Maybe we go to 20. That was your next guess. Notice that your lines are getting closer together. So we can manipulate and actually closer together and a lot higher. So maybe this time we go ahead and change your Y max as well. So let's say you then tried 30. You can definitely see it's getting a little closer. And let's change your Y max. If we're at 6, maybe we go ahead and try maybe 12. Let's try that. And we do see a clear intersection. Now, if I just tap my graph, notice that it does give me my special feature, and I'm just going to touch it, and it says 24,9. So your solution is your x-intercept typically, but this is your intersection of the two lines. So this is going to be your x value, 24. All right, let's try it again with your other graph here. So we have y equals, and we are going to say this is 2x minus 3 divided by 5, and we have x divided by 3 plus 1. So those are your two equations. Now we can hit your graph button, and this just being a standard window, we can notice again, we are trying to get further right. So let's try those processes again. We said we manipulated the 20. I might not change my X scale. Notice that your graph is getting us closer together. So your next window we tried, we said we went to 30. And we also changed your Y max on that one to 12. And you can see a clear intersection. Now, unlike Desmos, I can't just tap and go. You certainly can kind of use this tracer to get a best guess, but we definitely want to get as close as possible to that point. So let's go ahead and hit second trace all the way down to intersect. Oh, this is why I'm going out of this app and more onto Desmos. It just annoys me so much. Second trace, intersect. Now it says left bound. So the clear thing on this one is I need to see an intersection to be able to do a left and right bound. Now we want to get a little bit closer to where you believe your intersection is. So perhaps somewhere over here, we want to get to the left of that intersection. And then to the right. Now it's a little unclear as to where this intersection is going to happen. So I want to get to where I can tell they are no longer intersecting. And then enter. So notice that it says at the very top, 24 is your X and Y is 9. Now I'm going to write that down here. 24, 9. And that 24 is going to be your solution. Because notice that it says X equals 24, so therefore it is your X value. Now, other names for x-intercepts are solutions, roots, and zeros. So those are interchangeable. I cannot say that word. They are interchangeable. And so when we're asked to find a zero, a solution, an x-intercept, right? They're all going to be asking the exact same thing, just using a different word for it. So let's find your zeros. So to find your zero, we set f of x equal to 0. That's another word for your x-intercept, where we have x as some number that we don't know and y as a 0. F of x is another way to say y, and you have your x and y coordinate. So we set it equal to 0. We have 13x minus 39, and we're going to solve it as we normally do. So we can add 39 to both sides and then divide by 13, and we get x is equal to 3. So now if we were asked to find the x-intercept, well, now it's actually clearly stating, hey, it's an x-intercept. We're going to do the exact same thing. X-intercept being some number and y is 0. So it looks the exact same, even if the question is structured a little differently. We're going to solve it in the exact same way. Okay, find the solution of your equation. Again, the solution meaning your y value is 0, while x value is some number. So y is 0, 13x minus 39. Again, throw that 39 over. Just a different format on how to ask your question. And we're going to keep getting the same answer. Now, what does f of x is equal to 0 mean? Well, this is just another way to say your root, solution, your 0, and your x-intercept. So if you're ever asked for this value, it is just one of these interchangeable values or interchangeable words. Now, let's have you work on some practice. See if you can pause the video and either do this algebraically or graphically. So I might do the first one algebraically. Actually, I want you to get pretty efficient with the graph. So I might do these graphically to show you. So you have 14x minus 24. Let's do it on here. Less adds. Y equals 14x minus 24. And your next one, we said y equals, I want to say it was it 9 or 3? 3. 3 parentheses 9 minus x. Okay, so your graph, we want to figure out where they are intersecting. So if I want to change my my window, notice that I have to get a lot taller. I kind of like the placement of my x-axis, so I won't change that. So if I just need to get taller, I need to change my highest y value. And let's change it to 25. Oh, actually that worked out pretty nicely. So by changing it to 25, I'm just going to hit my graph, and my intersecting point is 318. Let's try it again for something a little bit more advanced with a lot more fractions. So 3t over 4 minus 2. Oh, so sorry. Y equals, and t is just your variable. So we're just going to hit 3t or 3x divided by 2. I believe it was 2. Nope, 4. Plus 2 minus 2. Okay, so that's one of ours. And then we have another, y equals, okay, so we have those two graphs. And we don't need to change your window. If we don't want to, we can clearly see the intersection of -4, 5, but let's just give it a practice. Maybe we want to center that value there. So notice that I would like to go a little bit further down and to the left, down being my y axis, my y minimum. So maybe we do something like -12. Do I like that? Oh, let's get a little bit further down. I want to center it just a little bit more. So maybe I even just match my y value from before. Now I still perhaps want to get a little more to the left meaning my y, my x minimum. So maybe something like 20, or maybe as well, I match it to the other one. So here you have your special feature, that intersection being the primary focus. And there you go. I really do encourage you guys to try it on a graph at some point if that is not your go-to, just to double check your work. All right, now let's look for some word problems. For an example, it says the average reading score on the National Assessment Test is given by y equals 0.155x plus 255.37, where x is the number of years, not ears, years, after 1970. In what year would the average reading score be 259.4 if this model is accurate? So we have to pause and really understand what one of these sentences is meaning. It says where x is the number of years after 1970. Now this sentence is super key because they are telling us that for the year 1970, x is going to represent a particular number. We are starting the clock. So we actually haven't started the clock quite yet on the year 1970. So we're going to use 0 as a placeholder. So when x is equal to 0, we're really referring to the year 1970. So if we're asked to find your values, your x value. Oh, so actually, before I do that, let me flesh this out just a little bit more because this is perhaps one of the first times we're seeing this sentence. So if we're being asked, well, what does x is equal to 1? What does that actually mean? What year is that? That's really just 1971. Let's do it again. What about when x is equal to 5? Well, that would be 1975. So hopefully that makes a little bit more sense because we're going to be analyzing what your final answer means when it comes out. So if we know that y is a reading score, and x is equal to a year. So if we have y is equal to 0.155x plus 255.37, and we want to know, well, what year? We don't have your x, but we do have a reading score of 259.4. Okay, so if we have your reading score, but we do not have the year in which it was achieved, we can either enter this in algebraically just as we've done in the last few problems. If we wanted to do it, if we wanted to do it graphically, we can do it from before, or if we wanted to do it algebraically, we certainly can as well. So notice that we want to isolate this x value. By doing so, again, we can't just divide by this value first. We need to take care of your constant. So we can subtract this value to the other side. So we have 4.03 is equal to 0.155x. Now that your x value is all alone, we can go ahead and divide by that number. Where x is equal to 26. Now, are we in the year 26? No. So instead, we have to figure out, well, what year was this achieved? So we need to know, okay, a little further down, we will have an x value where it's 26. So what year does that mean? Well, to go from 1970 to 1971, what did you do? Well, we added 1 to get to the next value. Or what about from 70 to 75? Well, we added 5. So what are we going to do if we need to go from 1970 to this next value? Well, we should be adding 26. So 1970 plus 26 comes out with 1996. So in the year 1996, we achieved a score of 259.4. So be able to bring meaning to your answer. So I'm going to write your answer one more time, or the context, the average reading score in 1996 is or was 259.4. Big takeaway is this sentence where X is the number of years after 1970. We're starting at the year 1970 and then ticking upwards. So now let's try it again with your next example. It says using data from 2000 and projected to 2025, the percent P of the US population that uses internet can be modeled by your equation, where X is the number of years after 1990. When will the percent be 99.61% according to this model? Pause video, see what you can come up with. So again, we're talking about the year after 1990. So X is equal to what for the year 1990? Well, we're starting at 1990, so X is going to be 0, which means if we have X1, that is going to be 1991. Or X is equal to 2 is 1992. So again, whatever your number comes out to be, we're going to have to manipulate your answer. So we are given P is equal to 1.19x plus 57.96. We know X is a year. What is your Y? Well, it's the percent of US population that uses internet. So that's kind of wordy, so we can just say Y is internet users, percent internet users. So if we have your equation, we now need to figure out, well, what percent did we want to look at? Well, we have 99.61% is equal to 1.19x plus 57.96. This being your initial percentage. So again, let's subtract out your coefficient. We should get 41.65 is equal to 1.19x. We can divide. And X should be about 35. Now, with it being 35, what does that mean in the context of your problem? Well, it's not the year 35. Instead, what would we have for your year? We said, well, we're going to add 1990 plus 35, and that should be 2025. Now, see if you can come up with a good sentence to round out your answer. In the year 1995, oh, sorry, not 1995, 2025, we will have 99.61% of US internet users, or 99% of the population of internet users, or some variation of that sort of sentence. And I believe that is it for chapter 2.1. Again, getting comfortable with your word problems is key. If they're telling you, if you have multiple variables and they are telling you word for word what these variables, like where to put the variables, definitely sub them in first, see if they can combine in any way, and simplify it so that you now have some equation that's more of a linear equation. Now, you're free to hop off of this video. In case though you wanted to do these two equations algebraically, please feel free to stick around. Okay, so first thing on part A, we notice that one side of the equation looks good, the other side has a parentheses. So we're going to go ahead and distribute in. We have 27 minus 3x. We have 14x minus 24. And let's go ahead and combine your like terms. So we're going to add your 3x to the other side, where we get 17x on one side. And let's go ahead and add 24 to the other side. Oops, so that actually cancels over here. There we go. No, I'll just keep that there. So we have, let's see, that's 11, that's 51, right? So 51, 17x. So then let's go ahead and divide by 17. So x is equal to 51 over 17. Those are a little unusual numbers. So let's see if we can, come on, 51 divided by 17. 3. There we go. So x is equal to 3. We can also plug it back in and double check, just like we did in our previous lecture video, just to make sure that both sides are in fact equal. And you notice that that 3 is the same as this 3 over here. Okay, so now let's try it again with these two what are these called? These two equations. Notice that if you wanted, because you have the -2 and a +2 on either side, we can feel free to add or subtract the 2 to the other side so that it's just one less term that we have to find a fraction for. It's not a necessary step, but it does make your life a little bit easier. Now, because we're working with a whole number, think about changing this to have a fraction, so just putting it over 1. Now we need to find a common denominator or a least common multiple to multiply them all. So either doing one or the other format for this method. I'm probably going to stick with maybe this one because I just cancel and go. Otherwise, if you like this one, just multiply both sides, multiply everything. Okay, so the least common multiple is 12. We can also do that by multiplying all of these values here. So if I multiply this 4 by A3. What I do to the bottom, I do to the top. I want to put parentheses around here too. That'll get me to 3 times 3t over 12. That is what I need on the bottom. I'm going to do it again to my other terms. I'm going to be multiplying this 3 by A4 and this 1 by A12. So you have 4, 5t minus 1 over 12 plus, let's see, that is 48 over 12. All of your denominators match, so we're going to get rid of them. And then we have 3 times 3t is equal to 4, 5t minus 1 plus 48. And then let's go ahead and distribute. So we have 9t is equal to 20t minus 4 plus 48. Combining some of your like terms on one side plus 44. Now let's go ahead. And I'm just going to rewrite for a second. 9t is equal to 20t plus 44. And let's go ahead and subtract your t to the other side. We get negative 11t is equal to 44 and divide out that negative 11. T is equal to a negative 4, which matches with the previous solution. So algebraically, if you wanted to do it algebraically, perhaps you're doing it with this in mind. So whether you distribute your parentheses or throughout your parentheses, or you need to come up with a common denominator, just make sure you're getting some practice.